Hello everyone. In this video, I'm going to talk about functions and graphs, which represents chapter 1.2 from our textbook. I'm going to introduce here the basic concepts of functions that we need to know in order to proceed through this chapter, and also talk about the related graphs of a function. So to begin with, we will first discuss what a relation is and the two terminologies associated with the relation called the domain and the range. We are going to talk about functions and determine what makes a function, or rather what makes a relation a function. All right, a function is a special kind of relation, so not all relations are functions. So we have to understand what the difference is between a relation and a function. What is the criteria necessary to make a relation a function? We are also going to talk about how to determine whether an equation, in other words, how to determine from an equation whether it's a function or not. We are going to learn how to evaluate a function and maybe go into graphing functions by plotting points. The rest of these topics on this slide, I think I'll put together a separate video for that so that it doesn't become too long and I lose your attention. Okay, so now to go. So here we have a definition of a relation. All right, a relation, it says a relation is any set of ordered pairs. The set of all first components of the ordered pairs is called the domain of the relation, and the set of all second components is called the range of the relation. All right. So since that's a mouthful, let's just break it up into parts. Let's just start with understanding what ordered pairs is. You may have already studied that in a previous algebra course, but let me give you a refresher, quick refresher. An ordered pair is written as two values within brackets, with uh, actually two variables within brackets. The first variable is x, and then the second variable is y, and they are separated by a comma. All right, so the first variable, or the first, also called the first component, is always the x value, and the second component, all right, and the second component is the y value. All right, now these x and y values come from a relationship. Okay, so x can be any value which is a real number. So x can be any value which is a real number, but the y value will depend on what value is chosen for the x. So there's a relationship between x and y here. All right, there's a relationship between x and y, but how is that relationship defined? The relationship is defined by what is called an equation. Okay, it can be any equation, but let's take a simple one here. Y equals x plus 3. So in this equation, what it says is you can plug in any value for x, which is a real number, add 3 to it, and you will come up with a value for y based on this equation or this relationship between x and y. So the relationship is defined by that equation. Keep that in mind. And we can plug any value for x and come up with a value of y. But the y value will depend on what value you choose for x. Okay, so if we choose -1 for x, all right, let's say x equals -1, then y equals, just plug in -1 for x, add 3 to it, and we get -1 plus 3 is 2. So we can write our ordered pair as when x is -1, y is +2. All right. We can choose another value for x, maybe x equals 0, and then again evaluate the equation or the expression here, y equals 0. Just plug in the x value of 0 into x, add 3 to it, and we get a y value of 3, and we write it as an ordered pair as 0, 3. Let's choose a positive value for x, make it x equals 2, and y will be 2 plus 3, which is 5. So our ordered pair is 2, 5. So the way we read these ordered pairs is when x is -1, y is 2. When x is 0, y is 3. When x is 2, y is 5. How do we know that? We know it by applying the equation on the different values of x. All right. Now, it says over here the set of all first components of the ordered pairs is called the domain. So that means all the x values in our ordered pairs are called the domain values. Domain values are also called input values, right? So domain values, they represent the first components, and it's basically all the x values. The x values, and the range values, as it says in the definition, the range values are the set of all the second components. All right, they are all the y values. They are all the y values. So when they ask you to list all the domain values, all you do is you just list all your x values within parenthesis, within curly brackets. So this is an x value, all the x values, the first component values. So basically you are picking -1, 0, and 2 and listing them as the domain values, -1, 0, and 2. Those are your domain values, your x values, and your range values would be 2, 3, and 5. All your y values, all your y values. All right. So that's the definition of a relationship and how to identify the domain and the range of a relation. So this is an example on how to find the domain and the range of a relation from a set of ordered pairs. So here we have 1, 2, 3, 4, 5 ordered pairs. Okay, a set. A set is always encapsulated in curly brackets. All right, as you see, these are ordered pairs surrounded by round brackets, but then the whole set of ordered pairs are surrounded in curly brackets. So the question is, find the domain and range of the relation. So as we know, the domain represents all the x values and the range represents all the y values. So all we need to do is pick all our x values and list them as domain. So 0 is an x, is a domain, 10 is a domain, 20 is a domain, all the first components of the ordered pairs, 30 and then 40. These are all the x values, and the y values are 9.1. They will represent our range values, 6.7, 10.7, 13.2, and 21.2. These are all our y values. So all you do is pick all our x values 0, 10, 20, 30, 40 and list them here, separated by commas and surrounded by parentheses, and the range values, which are all the y values, 9.1, 6.7, 10.7, 13.2 and 21.2, they are all listed. Again, all the y values are listed together, surrounded by parentheses, separated by commas, then those represent your range values. It's as simple as that, all right? As long as you know the domain are all the x values and the range are all the y values, then it shouldn't be a big deal to answer this question. Okay, now we are going to talk about a function. A function is a relation. However, it's a special kind of relation. It says here a function is a correspondence from a first set called the domain to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. All right, so now let me explain this a little bit. A function, like a relation, produces an ordered pair. So it will give us an x value and a y value, where x value, all right, an x value will be the input value, that is a domain value into a particular equation. And once we plug in that x value into that equation, it'll give us a y value, right? It'll produce a y value. So it does produce an ordered pair. However, in a function, we cannot have the same x value producing two different y values. So we cannot have one x value. Let's say we let's say we have a particular value of x which is 2. Okay, let's say we choose a value of 2. Now when x is 2, we plug it into a particular equation called f of x. It cannot produce, a function should not produce two different y values. It cannot, for example, be 3. Okay, the y value cannot be 3 as well as 5, for example. All right, so each unique x value maps to a unique y value. All right, you cannot have the same x value mapping to two different y values. All right, so we are going to talk in future slides some more about the properties of a function and how to determine from a graph, from an ordered pair, or from uh, an equation whether a relation is a function or not. Now here we have an example where we are asked to determine if a relation is a function or not when we are given some ordered pairs of a function. We are not given the equation here. We are just given the ordered pairs of a function, and the question is determine whether the relation is a function. Now we learned that in order for a relation to be a function, an x value, okay, let's just write the property here, every unique x value produces just one y value, a unique y value, right? That's the important property that makes a relation a function. All right, so we have to look at these ordered pairs and see if a particular x value maps to two different y values. So here we see there's one. Let's look at all the x values. We have x, 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 and x. So 1, 3, 6, 8 for our x values, and 2, 4, 5, and 5. All right, for our y values. So we see 1 maps to 2 here. We don't have any other ones for x values, so we are good. Look at 3. All right, we have a single 3. All right, there's only one ordered pair with a 3 for x here. Is there any other 3 for x values? No. All right, then we have a 6 for x value and an 8 for x value. All right, so we see that each unique x value maps to a different a unique y value is how I should say it really. So 1, 2, 3, 4, 6, 5, and 8, 5. All right, even though y is repeated here, all right, in the third and the fourth ordered pair, we have 5, the same value 5 for y, but that 5 maps to different x values. All right, it's not that the same x value is mapping to the to two different y values. So note the difference between the two. We can have the same y value. We can have the same y value mapping to two different x values. That's fine. Here, 6 produce where 6 produces a 5 and 8 produces 5. It still is a function. But if we had something like, let's say if we had 6 comma 5 and 6 comma 8, it would be a problem. It would not satisfy the property of a function. All right, we cannot have the same x value mapping to two different y values in a function. This would violate the property of a function, but this is fine. All right, what we have here, 6 mapping to 5 and 8 as an x value mapping to 5, that's perfect. That's not a problem. Okay, so I just wanted to point out the situation where you can have the same y value appearing twice or thrice as long as it's associated with a different x value. So let's read the solution here. It says no two ordered pairs in the given relation have the same first component, same x value. First component means x value, and different second component. So it's not that the same first components are mapped to different y values. All right, that's the relation is a function. So the given ordered pairs show that the relation which produce these ordered pairs is indeed a function. Now we are going to talk about how to determine functions from an equation, from a given equation. So just remember that in order for a relation to be a function, the same x value cannot produce two or more different y values. Okay, one x value can produce, a particular x value can produce only one y value. All right, it cannot, the same x value cannot produce two different y values. So the way we go about determining whether an equation represents a function or not is we take the given equation and we solve it for y, right? we solve it for y, and I'll go through an example in the next slide to show you how the process is for that. So we solve for y, and then we see whether we are getting two different values for y. So here it says if an equation is solved for y and more than one value of y can be obtained for a given x, then the equation it violates the definition of a function. So it does not define y as a function of x. Okay, so here is an example of how we can uh, determine whether a given equation is a function or not. So here we have been given a particular equation, x squared plus y squared equals 1. All right. So what we do first is we solve this equation for y, which means y has to be by itself on one side. We solve it in such a way that y has to be on the left hand side and everything else goes to the right hand side. It has to be something like y equals something. All right. So we have to first solve the equation. Let's do that. We have x squared plus y squared equals y. So we have to isolate the y. Y has to be by itself on the left hand side. Everything else must move to the right hand side. So we have to move x squared over to the other side. So we'll do it step by step. We first isolate y squared. So we have to move x squared to the other side. So what we do, let's start from here. Okay, I'm going to rewrite the equation here. X squared plus y squared equals 1. So I will isolate the y squared and move this x squared over to the other side. So it's going to be 1 minus x squared, right? When we move a positive x squared to the over to the other side, the positive becomes a negative, right? So that's why I have 1 minus x squared. So now we have to get rid of the square on the y. All right, we have y squared. We want it as y equals something. All right, we cannot have it as y squared. All right, it has to be y equals something. So to get rid of the square on the y, what do? We take the square root of both sides, right? We take the square root of both sides, which makes this the square root of y is y, square root of y squared is y. All right, equals, however, whenever we write a square root, all right, whenever we put a square root, we have to put a plus minus. All right, so we get plus minus square root over 1 minus x squared. All right, so here we have two values for y. All right, you see over here they did the same thing. um, they have given us a solution where they do exactly the same thing, but I just wanted to show you the steps here, walk through the steps. But what this means is y can be equal to plus square root over 1 minus x squared, or minus square root over 1 minus x squared. So it can take two values. Okay, and that's where it violates the property of a function. Okay, a single x value cannot have or cannot produce two different y values. So what it says here is the plus minus shows that for certain values of x, there are two values of y. For this reason, the equation does not define y as a function of x. All right. Okay, this is a quick review of the function notation. The way we write or represent a function in mathematics is f and then within brackets f of x. All right, so this reads as f of x. Sometimes they also refer to it as f at x, but this is the most commonly used form of representing a function. All right, f of x, that which means f of x equals a particular equation. All right, it will be on the other side. We will have an equation, and this x within brackets, all right, when we say f of x, this x within brackets will represent an input value that will feed into the equation and produce a y value. Another thing to note is f of x is the same as y. Okay, so have to keep that in mind, that y and f of x are the same thing. Only when the equation is a function, then we replace the y with f of x. All right, but f of x and y essentially is the same thing. All right, so when you see f of x instead of y equals something, then keep in mind that f of x is replacing y, and it's telling us that the equation is a function. That equation will produce every x value will produce a unique y value. All right, it satisfies the definition of a function. Here we learn how to evaluate a function when a given value is provided to us for x. All right, so here it says if f of x equals x squared minus 2x plus 7, evaluate f of -5. So that means what they want is they want us to plug in -5 for x and resolve this expression. Okay, that's all it is. All right, you have to plug in -5 into x and evaluate this expression. So what they do here is, they have given us f of x equals x squared minus 2x plus 7. You see, they have given us a specific value, although x can take any value, but they want us to evaluate this for just -5. So we replace x with -5, and throughout this expression here, x squared minus 2x plus 7, we replace our x's with -5. Okay, so this becomes -5 squared and then -2 times -5, and always make a habit of using brackets, because especially if x is a negative value and it needs squaring, if you miss the brackets, you may just square the 5 and not the negative sign. Okay, you see, -5, all of it with the sign is squared. All right, so because when we square a negative value, it becomes positive. It'll make a big difference in your calculation. All right, so just use brackets whenever you can. All right, it'll keep you on the right track. So -5 squared, whole squared, -2 stays as it is. It's a constant here, and the coefficient of the second term. And then again we replace x. Wherever there's an x, replace it with the given value. -5, again you see they put the -5, they surrounded a -5 in brackets, plus 7 stays as is, and now they do the computation. -5 squared is positive 25. All right, -2 times -5 is positive 10. Okay, be very careful with your signs. And then plus 7, so 25 plus 10, 35 plus 7, 42. So your answer is 42. So the way you write it is f of negative 5 equals 42. So that's how you evaluate a function. And the function can be anything. This was a quadratic function, but it can be a function with a square root in it. It can be a function with a, um, uh, uh, it can be a rational function. It can be anything. We will learn those later on. Graphs of function. Now here we'll talk about how to draw graphs of a function from its ordered pairs. Now, at the beginning of this video, I had said that I would create a separate video for some of the later topics, but I think I will just keep it as one video to maintain some continuity. Okay, so we'll talk about how to graph a function from its ordered pairs, and we will go on to an example to show how it's drawn in the next few slides. Okay, so here is an example where we are given two equations, two functions. One is called f of x equals 2x, and the other one is g of x equals 2x minus 3. And we will have to plot the points and connect them in order to graph their functions. So the first thing we do is pick some values for x. All right, you can pick any values for x. X is the independent variable. That means you can pick any real number for x. So what they do is they choose some negative values, they choose a 0 and then some positive values, and they run these x values, they plug in these values into the function to come up with a value for y. Now keep in mind that y and fx are the same, they refer to the same thing. Y is the same as f of x. When we refer to y as f of x, that means it tells us that the function that the equation, the given equation is a function. That means that every x value will have a unique y value. That means, in other words, uh, uh, a particular x value will produce only one y value. The same x value cannot produce two different y values, is what I mean. That is what makes a function a function. Okay, uh, but here let's go back to how we are constructing or plotting our or getting our ordered pairs to draw the graph. So we start with -2. Once we pick our different values of x, we start with -2. Take this -2, plug into x. So 2 times, let me try to get my pencil here. 2 times -2, all right? And always please use brackets, all right? Because otherwise, instead of when we use brackets, it reminds us that it's 2 times -2. If you forget to use your brackets and just write it as 2 -2, then you might end up subtracting the 2 instead of multiplying it, all right? So always use brackets whenever you can, all right? It keeps you on the right track. So 2 times -2 is -4. The next value for x is -1. So 2 times -1. All right, next we plug in -1. So 2 times -1 is -2. So that's how we get all the y values when it's 0. When x is 0, 2 times 0 is 0. When x is 1, a positive 1, 2 times 1 is 2, and then 4. So we get our ordered pairs here, -2, -4, -1, comma, -2, 0, 0. Okay, so you get the pattern, and now we have to go to our graph, to our coordinate, rectangular coordinate system here, and we need to plot the points that we got, the different ordered pairs. So the first one is -2, -4. So we have to find an x value of -2, and then the corresponding y value is -4, which is here on the lower y-axis, is where all the negative values are. So -2, -4 is here, so we just put a point here. The next one is -1, -2. So that means when x is -1, where does -1 appear on the x-axis? Between 0 and -2, correct? So somewhere in between 0 and -2, we have -1. So when it's -1, the y value is -2, which is here. So the next point is located here. We mark it with a point. Then we have 0, 0 right here. 1, 2. When x is 1, y is +2. Okay, and then when x is 2, y is 4. All right, so we got quite a few points, 4 or 5 points, which are adequate for us to draw, to get the graph of a line, and just connect the points and extend the line to either end, showing that it extends indefinitely um, on the upper end as well as the lower end. Okay, for the other line, for the graph of g of x equals 2x minus 3, it's a different equation, but the process is the same. Again, we choose some x values, some negative, 0, and some positive. So -2, -1 for x, 0, 1, and 2. We plug each of these values into our equation here, into our function. So when x is -2, all right, it's 2 times -2 minus 3. Again, use your brackets. I can't say that enough times, but please just make sure that you don't make computational mistakes. So 2 times -2 is -4 minus 3 is -7. When x is -1, again plug in -1 for x. So 2 times -1 minus 3, -2, minus 3 is -5. When x is 0, 2 times 0 is 0, minus 3 is -3. So that's how they get all these values. When it's 1, it's -1. When it's 2, it's 1. I guess I'm sure you not by now you understand how it works. And then once you plot these points, so when x is -2, y is -7. So let's go to -2 and find -7 on the y-axis. So that's between -6 and -8. So somewhere right in between the two. So -2, this here's a point, or mark it with a solid dot. All right. The next one is -1, -5. So -1 on the x-axis is between 0 and -2 here. So -5 again is somewhere between -4 and -6 on the y-axis. So here's our point. When it's 0, when x is 0, y is -3. So 0, -3 would be in between -2 and -4. And then we keep going with these other 2 points. All right, 1 and -1, 2 and +2 and +1, 2 and +1. And once we get all these points on the system, on the coordinate system, we just connect them with a straight line and extend on either side. Okay, so that's about graphing functions. Now here's how to determine from the graph of a function whether it represents a function or not. So we are not given an equation, we are not given an ordered pair, we're just given the graph, and we have to tell from the graph whether it is the graph of a function or not. So the test is called, the particular test for graphs is called the vertical line test for functions, and pretty soon you'll realize why it's called the vertical line test. It says here, if any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. In other words, if we draw a vertical line goes up and down, right? So if we are given a graph and we draw some vertical lines through the graph, and if we see that it intersects the graph at only one point, that tells us that it is a graph of a function. I'm going to go into an example. So let's go. So here we have an example to perform the vertical line test. So we're given two graphs. One is a parabola, a U-shaped graph opening horizontally, and the other one is a U-shaped graph which opens up, right? So how do we perform a vertical line test to determine whether these graphs are the graphs of a function or not? All you do is draw some vertical lines, all right, not a slanting line. It has to be a vertical line. So draw some vertical lines through the graph at different places. Okay, if the line intersects the graph at more than one point, then that means it's not a function. It's not a function. So here, all these three lines we see are intersecting the this graph at two different points, right? One here, one here, one here, one here. So that means it tells us that every x value here has two y values. Okay, this x value here has a y value up here and a y value down here. Same thing here, this x value has two y values, which violates the definition of a function. Going to the next one, which is an upturned parabola, a U-shaped graph, we perform the same test. We draw some vertical lines. They already drew a vertical line here, the blue line, and we see that it intersects it at one point somewhere here. Okay, there we can draw a few other lines. Okay, maybe another vertical line. It intersects, it intersects at one point on the graph, right? You can keep drawing several vertical lines and you will see that it intersects the graph at only one point. Therefore, it does satisfy the property, the condition of a function, and therefore this graph, the second graph is that of a function. The first one is not. Okay, the first one is not. Okay. Another exercise that we will be expected to perform with graphs is to analyze a graph and read it and then interpret it. Okay, so we will be given a graph, and just a graph, no supporting equations or ordered pairs as such, just a graph, and we will be expected to analyze it, read it, and interpret it. Okay, So here we have a graph given. It says it's about T cell count and HIV infection. Okay, so on the x-axis, we have to kind of understand what the x-axis represents. It says time after infection, infection of HIV, HIV infection, and along the y-axis represents average T cell count per milliliter of blood. Okay, so um, after being what it means is after getting infected by HIV, the um, T cell count drops for a period of time. Okay, so that's what this graph is representing. And then it says in the question, use the graph to find f of 5. That means these are the years. So 1 year, 2 year, 3, 4, 5 years, and so on, all the way up to 11 years. So when it says use the graph to find f of 5, now this 5 represents x, right? This 5 represents x, f of x. They've replaced the x with 5. That means we have to look along the x-axis. So here we have 5 on the x-axis. So they are saying that what would be the y value when x is 5? When they say f of 5, that means what is the y value when x is 5? In this case, at 5 years, what would be the average T cell count? So all we do is we go up 5 until we touch the graph, and then we go across to the left to the y-axis and pick up where it touches the y-axis, which is 400. Okay, so f of 5 equals 400. We are not given an equation here where we can plug in a value of x and find a value of y. We have to read the graph, okay, and then we have to figure out what y is. So in this case, f of 5, we go up vertically along 5 until we touch the graph, and then we go horizontally to the left until we touch the y-axis, and then we check the value on the y-axis, and it's 400, so it's f of 5 equals 400. Now this one says for what value of x is f of x equals 100? So in other words, what they are asking here is when will y be 100? For what value of x will y be a 100? Okay, so we start with y here, and we have to find the corresponding x value. So in this case, we look along the y-axis for 100. So 100 will be between 0 and 200, 0 being the point of intersection between the x and y-axis. So it'll be somewhere midway between 0 and 200. So let's say it's here. So now we have to go across to the right until we touch the graph. Okay, so let me use my pen here. So let's say this is where 100 is. Okay, so let's go. Oops, it has to be a horizontal line, and I may not be drawing it exactly horizontally, but okay, so it touches somewhere here, and then we go down to the x-axis, and it's 9, right? It's 9. So when x equals 9, we get a y value of 0, or sorry, a y value of 100. Okay, but here we are reading it in the reverse order. We are first, because we are given the y value, we go down the y-axis, locate the y value, and then we go all the way horizontally until we touch the graph, and then we go down to see where it what the location is on the x-axis. In this case, it's 9, so our answer is 9, right? Now here we learn how to figure out the domain and range of a function from its graph. Okay, so domain means all the x values that could be input into the function. Range represents all the y values that could come out. Y values are the output values. So all the y values that could come out from the function. But we have to determine that by looking at its graph. So what does it say here? It says to find the domain of a function from its graph, look for all the inputs on the x-axis that correspond to points on the graph. And then to find the range of a function from its graph, to find the range, look for all the outputs on the y-axis that correspond to points on the graph. So let's go into an example because that will make it easier for us to follow. So here we have an example to identify the domain and range of a function from its graph. Now keep in mind the domain represents all the x values that can be input into the equation of a function, and range represents all the y values that can be the resulting output after we plug in a particular value of x into our function. Here we are given just a graph. We are not given the specific equation for this graph. They have given us the generic form of a function y equals f of x and its corresponding graph. To find the domain values, that's the x values, we first see what values of x does the graph extend along. So on the lower end, the graph is hinged at x equals -2. It does not extend beyond x equals -2 on the left-hand side. At the upper end, the graph is hinged at x equals 1. This is 1, right? So the graph does not extend beyond x equals 1. There are values. The graph extends through all values that fall between -1 and +1. So, the graph has a point over here. The graph has a point where x equals -1. The graph has a point when x equals 0. The graph has a point when x equals 1/2, between 0 and 1. But the graph does not have a point when x goes beyond 1, like 1.1, we cannot touch the graph. At x equals 2, we don't touch the graph, right? The graph extends only between x equals -2 and x equals +1, and all values that fall between -1 and between -2 and +1. So the way we write the domain, the way we express the domain, it can be done in two ways. All right. One is using the set notation, which is written inside curly brackets. It's surrounded. The set notation is surrounded in curly brackets, and it reads like this. Domain, which is x value, so we have to start with x, and then a vertical line, and the vertical line reads as such that. So let me see if I can write that here. This vertical line reads as such that. Now let me go back to my pointer. All right. So x such that x is a value between -2 and +1. It can be any value. It can take, x can take any value between -2 and +1. Now, why do we write it as less or equal to versus just less than? All right. The reason is the two ends are marked, the two ends of the graph are marked as round solid circles, solid circles. If the two ends were marked with hollow circles, as in, let me see if I'm able to write it. Okay, a hollow circle looks like this. If the two ends were marked as hollow circles, that means -2 and +1 are not included in the set. All right, that means it's not included in the set. But these are solid circles. They are included in the set. So that means less or equal to. So -2 less or equal to x, and x less or equal to 1. Okay. The other way of writing it is in interval notation, where we use square brackets to surround our endpoints of the interval. The lower end of the interval, we always start with the lower end. The lower end of the interval is -2, and the upper end is 1. And this comma suggests all values between -2 and +1. All right, all values between -2 and +1. Now, if these endpoints were hollow circles, then instead of square brackets, we would surround them with round brackets. Let me see if I can write the round brackets here. Bear with me, please. I'm trying to get my pen to work. Okay, it would be written as round brackets and then -2, comma 1. However, because in this particular example, it's not round brackets, it should be square brackets. So I'm going to, this is not the right answer for this particular example. But if it were hollow circles, then we would use the round brackets. Okay. All right, so that's about domains. Now we have to figure out what the range is. All right, so range means all the y values. So we have to look for the y values along the y-axis. So what's the lowest y value in this graph? The lowest y value is y equal to 0, correct? When x is -2, y equals 0. The graph does not extend beyond y equal to 0. Okay, it does not take a value less than 0. That's the lowest value that the graph takes for a y value. When x is -2, y is 0. The highest value that the graph takes for a y value is 3, correct? So when x is 1, we go up to the graph and then horizontally to the left to touch the y-axis, and this point is 3, correct? So y equals 3. So that's the highest value the graph takes. It does not go up beyond 3. All right, so the range of values for this function from the graph is a y value between 0 and 3. So the way we write it again in set notation is start with curly brackets, then y, then a vertical bars which read such that. So y such that y is a value between 0 and 3 inclusive. Why inclusive? Because again, these values, the endpoints of the graphs, are denoted by solid circles, which means that 0 and 3 are included in the output in the range values. So 0 less or equal to y. Now this is another example of identifying the domain and range of a function from the graph. All right, so let's look at the graph. We see that one end of the graph has a hollow circle, whereas the other end of the graph, okay, the right hand side of the graph has a solid circle here. Okay, so that's going to determine how we are going to express our domain and range. Okay, so now first let's look at the domain values. So for the domain values, we have to look for the x values along which the graph extends. So the smallest value that the graph extends to is -2. The smallest x value that the graph extends to is x equals -2. At x equals -2, y is 2, is at 2 really. The highest value that the graph extends to is +1. This is +1, right? So this is +1. The corresponding y value is -1. All right. So the way we are going to represent this is in set notation with curly brackets, x, such that this vertical line reads such that x is a value between -2 and +1, right? X is a 2 between -2 and +1. Now, on the left-hand side, -2 is not included in the domain. Any value which is greater than -2 is fine. All right, it's good to get included, but not -2. Why? How do we know that? Because of the hollow circle. That this hollow circle tells us -2 is not included, but any value which is greater than -2 should be fine, should be good to get included. Okay, so -2. That's why we just have less than, not less or equal to, unlike in the previous example. And then for 1, because 1 has a solid circle, we have less or equal to 1. All right, so this reads as x is any value between -2 and +1, but -2 is not included in the set, whereas +1 is included in the set. In the interval notation, note how they have represented it. Because we have a hollow circle at -2, we use the round bracket to include it, that it's to represent that -2 is not included. Whereas next to 1, we have a square bracket because we have a positive because we have a solid circle, which means that 1 is included in the set of domain values. How about the range? Okay, range means we have to look at the values along the y-axis, correct? So at x equals -2, y is 2, correct? Y is 2. So 2 is one of the y values at the upper end, or rather the highest y value that can be output from the function, right? The highest range value that we can expect to get. Whereas the lowest y value is at -1, correct? That's the lowest y value. So again, the way we write it, the way we represent the range in set notation, again, start with curly brackets or parentheses, y such that with the vertical line, -1 less or equal to 1. Okay, again, the lower value should be at the on the left hand side. -1 less or equal to y. All right, because -1 is a solid circle. Therefore, -1 less or equal to y, and y less than 2. Okay, but here we do not have less or equal to 2, we have just less than 2. In interval notation, it would be square brackets to the left of -1. Why? Again, because -1 is included in the set of range values, and then comma 2, and then the round bracket to represent that 2. We can go as high, as close to 2 as possible, but 2 is not in the set um, uh, of the range values. Okay, therefore the round bracket. Now the final topic uh, in this section is identifying intercepts from a function's graph. There are two intercepts possible in a graph. One is called the x-intercept. What is the x-intercept? X-intercept is when a graph crosses the x-axis. So x-intercept represents the point at which the graph intersects or crosses the x-axis. The y-intercept is the point where the graph intersects or crosses the y-axis, and it is possible to have for a graph to um, have more than one x-intercept. That means the graph can cross the x-axis at multiple points. However, the y-intercept of a graph is the graph of a function, that is, can cross the y-axis only once, at most once, or it may not uh, intercept the y-axis at all. So 0 or 1, not more than once. Otherwise, it's not a function if it is intersecting the y-axis more than once. So a function can have more than one x-intercept, but at the most, one y-intercept. Here's an example of how to identify intercepts, the x and y intercepts, from a function's graph. Now, keep in mind that at the x-intercept, at the x-axis, any point on the x-axis has a y value of 0. All right? At the x-axis, no matter where the point is, whether it's here or at this point or at this point, or at any point on the x-axis, the y value has to be a 0. Likewise, any point on the y-axis has an x value of 0, right? This is a fact. It never changes, all right? And this is a fact you have to remember, because you're going to use this, you have to use this important fact in order to find the x and y axis later on, all right, in later sections. So, but just from the graph, just look for the points where the graph intersects the x-axis and read the ordered pair at that point. So over here, this is an x-intercept, this is an x-intercept, and then we have 3 x-intercepts here. So the first one on the extreme left-hand side is x equals -3. This point is -3. X equals -3 Doesn't matter what the x value is, the y value will always be a 0. So it's negative 3 comma 0. All right. The next one is at x equals negative 1. This point here is x equals negative 1. So when x is negative 1, y is 0. Okay. All x-intercepts, no matter what the x values are, will have a y value equal to 0. All right, that's going to be true always. The third x-intercept point is at x equals 2, x equals 2, y equal to 0. For the y-intercept, the x value will always be equal to 0. So let's locate the point here. This is where the graph crosses the y-axis, and over here the y value is negative 6, but the x value will always be 0, so we write it as 0 comma negative 6. All right, so that's how we identify intercepts, x and y intercepts, by looking at a graph. Later on, we will learn how to find the x and y intercepts from an equation. All right. So I think that ends this section of chapter 1, 1.2.